Hello students, this is Chintan Patel and welcome back to the video lecture series of the fundamentals of machine design. So in this video you are going to look at the brief overview of the chapter number 1. So I will be showing you a PDF of the chapter number 1 notes which will contain the different concepts and the examples that you need to revise before the examinations. Although we have covered few concepts in the previous lectures and the previous videos, so that we will quickly revise those concepts in this particular PDF. Some of the new examples were included in this PDF so that you don't find it confusing while solving the examples in your examinations, and that is why I have made this video to clear out each and every concepts which were not included in the previous videos. Okay, so basically let's get started with the first topic of the chapter number 1. The chapter number 1 is clearly divided into 3 different topics. The first one is the simple stress and strain, the second one is the thermal stress and strain, and the third one is the elastic constants. So we are looking at the first topic, that is the simple stress and strain. So we will quickly go through the different concepts which were already covered in the chapter in the previous videos, like the definitions and the relation between the different terminologies. So basically this is the stress definition. The stress is defined as the internal resistance force set up due to the deformation per unit area, where if there is no deformation occurring on the body, then the resistance will not be offered by the body. Ultimately there will be no stress. So basically deformation is the reason for the stress. Keep that in your mind so that you will not get confused while solving any stress examples. So basically stress is the internal resistance force per unit area. The area is the one which is offering the resistance, or we can say that it is the resisting area or the cross-sectional area of the body. So basically this is the equation of the stress, that is the force R upon A. R is the internal resistance force which is equal to the externally applied load P. That's why we have written over here that is P by A. Okay, so this is the P by A, and the unit of the stress is Newton per mm square or kilonewton per meter square. So basically these are the units. The strength is the maximum limit of the stress that the material can carry. That is the basic definition of the strength. And we have also added a note over here that the stress is a variable parameter while the strength is the property of the material. So the property of the material doesn't get generally changed with respect to the time. Yes, it gets affected with the working condition and the surrounding, and that's why the strength usually will be the constant property. Okay, so basically we are going to move upward. Another definition which was already covered in the video, that is the strain. Strain is nothing but the deformation per unit dimension, or we can say that the change in dimension per original dimension. That is the strain definition, which can be denoted as a epsilon, and epsilon is formulated as a delta L upon L, and it is a unitless quantity that we all know about that. Now as you can see, the elastic limit is also another definition which we have already seen, that a limiting value of the force within which the deformation is entirely disappeared, or we can say that the material remove its deformation and get back to its original shape. Then that particular limiting force is known as a elastic limit force, and the stress corresponding to that particular force is known as a elastic limit stress. Okay, so basically this is the elastic limit. Now another concept is the Hooke's law. Hooke's law is the relation between the stress and the strain within the elastic limit. So if you are applying the force within the elastic limit, then the Hooke's law holds good. So Hooke's law is basically stress is proportional to strain, and in order to remove the proportionality you will have to introduce a constant which is known as a Young's modulus, or the modulus of elasticity. So Young's modulus is represented by E, which is having the same unit of the stress. Why it is having the same unit? Because if you write the formula of the Young's modulus, it can be written like this, that is the E equals to sigma by epsilon. Now if you write the formula, unit of the sigma, that is Newton per mm square, and the unit of epsilon is unitless quantity. So ultimately the final unit comes out to be the Newton per mm square for the Young's modulus. So the Young's modulus shares the same unit as the stress. So stress and Young's modulus are of the same unit. So that's all I wanted to tell you about that. One more thing I want to add about this, that is the for mild still. Mild still, we remember the value of the Young's modulus, and the Young's modulus for the mild still is written as a 200 gigapascal. Now this value may vary depending on the grades of the still. So in your examples they may give you another value for the mild still, because we all know that the still have the different grades. Okay, so in your example, if they have provided the value, particular value for the different types of the grade of the stills, then you must use that value. You don't have to remember this value and use it. But whenever in your example they do not provide any value for the mild still, then you will remember this value E and write it with the bracket assuming. Okay, so you will have to assume this value whether they provide it or not. In your examples, if they do not provide it, you will have to write it on your own. Okay, so you have to remember the value of the Young's modulus for the mild still. If they have not mentioned whether the material of the component is a mild still or not, then you will assume it also that the material of the component is mild still only. Okay, so if they do not tell you that which material is used or what is the Young's modulus for the material, you will go for this value, that is 200 gigapascal. Now this value is in the gigapascal, and we have converted into the megapascal by multiplying it by the 10 raised to 3. So as you can see, why we have converted it into the megapascal, because megapascal is an alternate unit of the Newton per mm square. So you can write Newton per mm square instead of the megapascal. Both are the same. Newton per mm square and megapascal, both are the same. So there is no worry about the megapascal. If you can convert the unit into megapascal, then you can directly write Newton per mm square instead of the megapascal. So that is the main conversion that you need to remember. Now the next thing is the equation of the deformation. In your example, they will frequently ask you about the calculate the value of deformation, calculate the value of elongation, calculate the value of the change in length. Each and every terms are represented by delta L. So the delta L equals to PL upon AE, that is the equation of the deformation. So PL upon AE is the equation using which you will be able to calculate the deformation value as well as the elongation value. Now we will move on to the next topic, and that is the axial load, transverse load. So if you take an example that we have introduced in this diagram. So this diagram is basically of the cylindrical bar or the cylinder. The axis of this cylinder is represented by the dotted line. So if you are applying the external force P in the direction of the axis, then this type of a load is known as a axial load. But if you are applying a load which is perpendicular to your axis, as you can see, the angle between your axis and the direction of the force is 90 degree, and that's why this type of a load is known as a transverse load. The another name for the axial load is a longitudinal load. Okay, so you can remember both the name, because in your examination they can use any name in order to confuse you. If you know those names, then you will be able to solve those examples. So longitudinal is nothing but the axial. Okay, so we will move another type of a bar. So what is bar? Bar is one type of a rod. Okay, so a rod which may have a circular cross section or a rectangular cross section. The shape of the bar is not defined. We can say any rod as a bar. Okay, so basically a prismatic bar. What is a prismatic bar? Prismatic bar is the bar which is having the continuous cross section area, which means it does not change, its diameter is not changing, its width is not changing, it has the continuous cross section area, and that type of a bar is known as a prismatic bar. So another bar which is a non-prismatic bar, as you can see in this diagram, the cross section area of the non-prismatic bar is continuously changing. So over here if you cut it, if you cut this bar from here and find the cross section area, you will find more area as compared to if here. If you cut it from here, then you will find a less cross section area value. Similarly, if you cut it from here, you will find a larger value as compared to here. Okay, so basically cross section area is the area which can be seen from the side view if you cut the particular bar. So this was the basic idea about the different types of the bar. Now we will move on to another topic, that is this one. So basically I would like to give you a brief idea about this type of examples. This is a one pattern of the example which are not included in the previous video, and that's why I have provided into your notes so that you don't get confused while if it is asked in your examinations. So what is the method to solve this type of examples? So basically the equations used in those examples are the same that we have already discussed in the previous videos. So the concept is the same, but the thing is you need to find out the different parameters which from the given data, and the given data is nothing but this diagram. So they will provide you this diagram, and from this diagram you will have to find out the given data. So basically this diagram is required for you, and you will have to analyze this diagram. To analyze this diagram, you must understand that this diagram is completely balanced diagram, which means not a single part of the diagram is unbalanced. Okay, so keep that in your mind. I will draw this diagram into another screen so that you guys can understand. Okay, so basically what we are looking at a bar, prismatic bar again. Okay, and here 100, 80, 50 and 30. Basically here is the 100 kilonewton, 80 kilonewton, 50 kilonewton, and the last one is the 30 kilonewton. Okay, so 80, 50 and 30. So basically these are the different terms. Now what we are going to do, we are going to separate each and every parts. So how are we going to separate each and every part? Based on the cross section area, first one, and the second one, the point at which the new force is applied, you are going to separate it from that particular point. Okay, so these two criteria should be remembered. First criteria based on the cross section area. Second criteria, the point at which the new load is applied. So as you see this particular example, there is no change in the cross section area. So the first criteria is not applied. But the second criteria, the point at which the new force is applied is this one. So we are going to separate this part alag. Okay. So we are going to consider only the left side of the part. On the left side of the part only one force is applied. And we are going to neglect the right side portion from the original diagram for now. We are not going to neglect it for the entire example. For now, particularly for part 1, we are going to neglect it for particular this time. So what we are going to do, we know that our entire diagram is balanced condition. So we are going to find out the balance over here. So if you consider this part 1, for the part 1, 100 kilonewton load is applied, and in order to balance it, we need to consider another force in opposite direction with the same magnitude, that is also 100 kilonewton load. Okay, so part 1 is balanced, and for part 1, P1 is 100 kilonewton, because this is the only force which is being applied for the part 1. So the part 2, now we will consider the part 2. But for the part 2, you need to start with this point and up to the point where the new force is applied. So this is the point where the new force is applied. So we are going to separate it from the original figure. So this is our part 2, and we are going to represent it over here. But for the part 2, if you notice, this is the face which is similar to this one. These both faces are the same. Okay, so in the original diagram there were no 100 kilonewton force applied, and that's why we cannot apply it over here also. So in order to nullify it, we are going to consider another force which is opposite to this one, in order to nullify it. Okay, so 100 kilonewton force is applied over here. Now we are going to consider the left side of the part 2 only. So the left side of the part 2 is this one. So this is the left side of the part 2, and in this left side of the part 2, one force is applied, that is 80 kilonewton. Right side also contains one force, that is 50, but we are not considering the right side for now. Okay, we will always consider the left side of the particular part. Okay, we will not look over the right side. So for this left side, there are two basically forces, 100 kilonewton and 80 kilonewton. Now as you can see, both the forces are in opposite directions. So we will have to subtract the smaller one from the bigger one. So our final force will be 100 minus 80, and the final answer comes out to be the 20 kilonewton. So 20 kilonewton must have a direction. Direction will be in the direction of the larger force. Which one is the larger force? Larger force is the 100 kilonewton, and it contains the direction of the left side. So our final force will be in this direction with the magnitude of a 20 kilonewton. So you are going to represent only final force. You should not represent these two forces. If you represent it, then it is only for you, for the calculation purpose. It is not for the examiner overview. Okay, so you can represent only the final force 20 kilonewton. So basically on the part 2, one force is applied, that is 20 kilonewton, which is the final force. Now in order to balance it, we need to apply a counter force which is in the opposite direction, 20 kilonewton. Okay, so this is done for the part 2. So P2 is 20, P2 is 20. Okay, similarly we are going to separate a third part. Third part is over here. Third part is over here. Now as you can see, this phase and this phase are the same, and there were no 20 kilonewton, and that's why we need to remove this 20 kilonewton by opposite force, that is 20 kilonewton. Now as you can see, we need to consider only left side of the part 3, that is 50 kilonewton. So there is a 50 kilonewton. So 50 kilonewton and 20 kilonewton both are in opposite direction. So the final force comes out to be 50 minus 20, that is 30 kilonewton. And what will be the direction of 30 kilonewton? In the direction of the larger force. So the larger force is 50. So you can represent the 30 by this. So this is the 30 kilonewton final force which is required to be represented. Now this figure should be balanced. In order to balance the figure, you will apply opposite direction 30 kilonewton force. So this 30 kilonewton will balance the figure, and this 30 kilonewton will match with the original figure. So this is how you can check whether your answer is correct or not. So basically these are the concepts without which you cannot solve the entire examples. So similarly, what we have done over here, we have represented one example so that you can quickly solve it. So first example is over here. In this example, they have asked you to find out the stress in each part and the elongation of the each part. The stress can be calculated using the formula force upon area, and delta L can be calculated using the formula PL upon AE. We know that. Okay. All you need to know is the particular force for that particular part. So basically from this figure we can easily calculate, we can easily understand that there will be 3 different parts. For each part you will have to find out the value of the separate force, and for that we are going to look into our diagram like this. Okay, so this is our final diagram. So final diagram will contain the different calculations. As you can see, we are going to consider only the left side of the part. On the left side there was a 20 kilonewton, and 20 kilonewton is balanced with the counter force. Now this 20 kilonewton is again balanced over here, and 40 kilonewton is taken from the left side. So final answer comes out to be 60, and 60 is balanced over here. So 60 is again nullified on this surface. There was no other left force, and that's why it is balanced like this. So basically we have each and every forces from the previous method that I have already discussed. From that you can easily calculate the value of the stresses, that is nothing but the force upon area. Area is easily available because the diameter of the particular rod is already provided. As you can see, this contains the diameters. So these are the diameters. As you can see, these are the diameters for each and every part. So diameters are provided from which we have calculated the area by the pi by 4 d square. Now we are going to look at the different other parameters. So other parameters which remains over here is the delta L. Delta L can be calculated using PL upon AE. Each and every parameters are already given. So if you put all the values in your calculator, you will get the answer as the 2.546 mm. As you can see, the entire part 1 is subjected to a compressive forces, and which will reduce the length of the part 1, and that's why we have written decrease at the answer of the delta L1. Similarly for the delta L2 and similarly for the delta L3, because all the lengths are decreased because of the compressive nature of the forces. So these were the different type of one type of example. Now we will look at the another type of the example, that is the steel rod of 30 mm diameter is placed inside a copper tube of the external diameter 50 mm. So basically what we are going to do over here is this. So if you consider this entire steel rod of the 30 mm diameter is placed inside the copper tube of the external diameter 50 mm. So a steel rod is represented over here. This is our steel rod which is having the 30 mm diameter. A copper tube of external diameter 50 and internal diameter 40 is also represented by this. This is our copper tube with the external diameter 50 and internal diameter 40. As you can see, the internal diameter of the copper tube is 40 and the external steel rod diameter is 30, and that's why there will be some gap over here. So this type of a material, both the materials are connected at the ends like this. So both the materials are connected over here, and as those two materials are combined together to create the one particular body, that is why this type of a connection or this type of example is known as a composite material example. Composite material. So why composite material? Because there are two or more materials are involved to create the one entire body. So this type of example is composite bar example. We will look another example of the composite bar later on, but first look at this example where two different materials were used. For those materials, Young's modulus will be different. For the steel it is different, for the copper it is different, but the diagram is represented from the given words or the given data which is already provided in your example. Now having the equal length of the 500 mm, so the length of the bar is 500 mm, connected rigidly at the ends. So at the ends we have connected both the material together. The bar is subjected to an axial force of 150 kilonewton. As you can see, we have provided an axial pull or externally applied tensile force of 150 kilonewton. Find the stresses in each material. In each material means in steel you will have to find another separate stress, as well as in copper you will have to find a separate stress. Okay, and elongation of the composite bar. As I mentioned, this is the bar which is named as a composite bar. So elongation of the composite bar is to be calculated. What is elongation? Elongation is another name of the deformation. Deformation is another name of the synonym of the change in length, and it can be represented by delta L. So if you need to calculate the delta L, you will have to know the parameters like the PL upon AE. Secondly, you need to calculate the value of the forces for the particular material, because you need to find the value of the stresses in those forces, like the sigma for the steel and sigma for the copper. So sigma is nothing but the force upon area. So you will have to calculate those stresses, and in order to calculate the answer of this example, you will have to first summarize what you have from the given data. In order to summarize, you know that the Young's modulus for the steel is given, which is 200 gigapascal, and Young's modulus for the copper is given as 100 gigapascal. Now if you just look at the diameters, then diameter will provide you the answer of the cross section area. So basically the cross section area can be calculated as for copper the cross section area can be calculated as a pi by 4 50 square minus 40 square. Why we have done this? Because if you consider the copper is a tube which is hollow from inside, and if you cut the copper and look from the side view, then the side view of the copper would look like this. Okay, so this is the side view of the copper. So basically we need to calculate this much area only. Then how can we calculate this area? By subtracting the inner circle from the outer circle. What is the area of the circle? That is pi by 4 d square. Pi by 4 50 square minus pi by 4 40 square. So this is our basically very clear understanding of our area calculation, that is the copper cross section area. Similarly, if you want to find out the cross section area of the steel, then steel is the rod which is not hollow. So if you cut the steel material and look from the side view, then it will look like this circular. Okay, so in order to find out this circular area, you can directly apply the equation, that is pi by 4 d square. And we know the d value for the steel is 30, and that's why the cross section area of the steel is provided as a 706.5 mm square. So now remember, for the case of the composite bar, in case of the composite bar, you will need two different steps in order to finish the example. The first step is this one, that is the strain for both the material is the same. Why the strain for both the material is the same? Because if you just look at the figure, you have the notes, right? So if you just look at the figure, then you will find that the original length of both the material are the same, and both the materials are connected together at the ends. So whenever you pull those two material together, then it will be elongated together. So the change in length for both the material will be the same. So delta L for both the same, and small l for both the material is the same, and that is why you can write delta L upon L for one material and another material. As all the parameters for both the material are the same, you can directly conclude that the strain for the steel and strain for the copper is the same. So this is our first step which you need to consider for in the case of the composite example. So instead of the epsilon, you can write in terms of the stress like this, because we know that the stress is equals to Young's modulus and epsilon. This relation comes from the Hooke's law, and we have used this relation in order to consider to reach up to this step. Now if you put the value of the Young's modulus and cross multiply it with this answer, then you will simplify this answer and get the sigma of steel, that is stress of the steel, equals to 2 times the stress of the copper. So this is our first equation, and we will put this aside. Now we will move on to another step, the second step and the last step of this type of example. In order to solve the composite example, you need to remember two different steps. The first one I have already explained. The second one is this one. So what is the second step? That is P, that is externally applied load, is equals to summation of the load required for the steel to be elongated and load required for the copper to be elongated. So this relation holds good for the composite material. Okay, when the material is composite, then you can apply this relation directly. Okay, so we do not need to find out the forces. We can directly convert it into in terms of the stress. How? We know the relation. We know that the sigma is equals to force upon area. We know that this relation. So in order to make the subject P, you can directly multiply A with the sigma. Then that is what we have written over here. Instead of the PST, we have written over here that is sigma ST into AST. Instead of the PCU, we have written over here sigma CU into ACU. And directly we have converted the 150 kilonewton into the Newton by multiplying the 10 raised to 3. Now if you just put the value of the areas that are already calculated in the previous page, then you can simplify this equation up to this point. Now this is the equation from the step number 2. Now if you merge the equation number 1 and equation number 2, if you put this value, if you put the equation number 1 into the equation number 2, you will find only one unknown, that is sigma Cu, and sigma Cu can be calculated from this equation, that is nothing but 70.77 Newton per mm square. So from sigma cu you can directly multiply 2 with the answer and get the answer of the sigma st, and from sigma st you can directly calculate the value of the delta st from PL upon AE. What is PL upon AE? P into L upon AE. How this equation comes up? Because P by A is known as sigma, and that is what we have written over here. Okay, instead of the P by A we have written sigma instead of the P by A. So if you put all this value you will get your answer as the example's answer. Okay, so this was the end of our example. We will see another composite material example which can be asked in your examination, and we will see that in this with the given data like this. As you can see, the given data says that a load of 200 kilonewton is applied on the short concrete column. Now what is the column? We know that each and every building has the column or a pillar, we say that. Okay, the column would look like this. Okay, this is our column or the pillar on which the building is supported. So basically this is the column which is having the 500 mm by 500 mm dimension. Now whenever they give you dimensions like this 500 into 500, it means that they are providing the cross sectional area. So if you cut this column, if you cut it from here, and look from the top view, your top view would look like this. This is the top view of your column. Okay, so this is the top view of your column, and the top view of the column is 500 mm by 500 mm, which means this side is having the length of 500 mm and this side is having length of the 500 mm. Basically this is the meaning of the given dimension. Reinforced with the 4 number of 10 mm diameter steel bars. Now we all know the pillar is made up of the concrete material inside which we usually insert the steel bar materials or the TMT bars in order to improve or increase the strength of the pillars. So basically 4 number of the bars are inserted, and if you cut it and look from the top view you can see those 4 number of bars with these circles. So these are the circle of the bars. Okay, so these are the circle of the bars. Now the diameter of the circle is already provided as a 10 mm, so we can calculate the cross section area and take the Young's modulus for steel is a 2.1 into 10 raised to 5 and for concrete is 1.4 into 10 raised to 4 Newton per mm square. So this is all about the given data. As you can see, the cross section area for the steel. Now steel bar are 4 number of bars. Each bar is having the 10 mm diameter. So if you calculate the cross section area of the one circle, then it comes out to be the pi by 4 10 square. But there are 4 number of bars, that's why we have multiplied with 4. So final answer comes out to be 314.15 mm square. Now another area which is calculated over here is the gross area. Now what is the gross area? Gross area is the area of the entire cross section or the entire square. So if you want to find out the gross area, then you can directly multiply the 500 by 500, that is 250000 mm square. Now why we have not considered it as the area of the concrete? Because this is not the area of the concrete, although it is the area of the square. It is not the area of the concrete because we have inserted 4 different rods into that particular square. You need to subtract the area of the rods in order to find out the area of the concrete. So this is how we are going to calculate the area of the concrete. Area of the concrete is represented by the AC, and as you can see, AC calculated from the subtraction of the A still from area of gross, and the answer comes out to be this. Okay, so this is our answer. Now we will apply our first step. Now what is the first step? The first step is the strain for both the material is the same. This is our first step. Now you can convert it in terms of the sigma. In terms of sigma, you will find this relation as your final answer after the simplification. Okay, so after simplification you will get this as a equation number 1. Now you will apply our second step. Second step is nothing but the P, total applied load, that is 2000 kilonewton, is equals to load taken by the steel and load taken by the concrete, summation of both the loads. Okay, now convert it in terms of the stress. you will get this answer, and put this value of the equation number 1 into this equation. So your answer comes out to be this. Now we know the value of the still area, we know the value of the concrete area, but we do not know the value of the sigma concrete and sigma concrete over here. So the sigma concrete is the only one which is unknown from this equation. So if you make it as a subject and calculate the rest of the answer, so if you make it as a subject and calculate the rest of your answer, then sigma C answer will be 7.86 Newton per mm square, and put this value in your equation number 1 to get the answer as a 117.9 Newton per mm square. So this is the end of our first topic note, that is nothing but the simple stress and strain. In the upcoming video I will provide you the notes of the thermal stress and the elastic constants. Till then, thank you.